Hi everyone, and welcome to our second TIA Centre seminar of the academic year. We're delighted to be joined in person today by Jack Breen. Jack is an imaging scientist at Perspectum, having recently submitted his thesis at the University of Leeds. With a background in mathematics and statistics, Jack's PhD has focused on computational pathology, given the vast digitisation programme undertaken in Leeds. With direct supervision from pathologists, oncologists, and computer vision experts, the project aims to develop and thoroughly validate clinically relevant AI approaches, specifically applied to the diagnosis of ovarian cancer. Jack has taken particular interest in conducting robust validations to reduce the high risks of bias and overly optimistic results associated with early prototyping studies. During this time, Jack has also received multiple scholarships from the Alan Turing Institute, and the title of Jack's talk today is Foundation Models and Multiple Instance Learning Methods for Ovarian Cancer Subtype Classification. Jack, thanks again for joining us. I'm ready to start.
Great, thank you. So hopefully you can all hear me online, so keep an eye on the chat just in case there's any problems with that. And yeah, I'll get straight into it. So yeah, a little bit about me to start with. So my background, as we just said, is in maths, so maths and statistics at the Uni of Nottingham. I've been doing my PhD and integrated MSc at the University of Leeds since 2020, so started during COVID. Yeah, as just said, I've just handed in my thesis, so just waiting for the Viva now. And in the meantime, a couple of weeks ago, I started a job at Perspectum in Oxford. So they were a spin-out company from the Uni of Oxford about 10 to 12 years ago. They were actually looking at liver MRI, still AI, and they are now sort of broadening their horizons into more imaging modalities, and that's where I fit in on the pathology side. So the focus here is ovarian cancer. So ovarian cancer is the 8th most common cancer in women worldwide, so it's 300,000 new cases each year, and it is unfortunately a very deadly disease, so it leads to about 200,000 deaths each year as well. So the reason it's such a deadly disease is because it's so hard to detect. So the symptoms that someone will get with ovarian cancer are often just confused for signs of the menopause. So these are generally post-menopausal women who will get ovarian cancer, and the symptoms will be really vague until it becomes really serious, so sort of stage 3, stage 4. And that's the point at which it'll get picked up because it'll have spread somewhere, it will start having symptoms that are a bit less vague, and by stage 3, it's already kind of too late to get a really good outcome. So what would be really nice if it could be detected at an earlier stage. Some people did look into that by screening, so screening by blood biomarkers and ultrasound. Unfortunately, 200,000 women were screened through this trial, not a single life was saved. So there was millions of pounds, decades of work put into this, didn't save a single life, which is why we do not currently screen for ovarian cancer. We don't have an effective way to do it. The other side of things is the pathology, obviously. So the pathologists are just overburdened. We know this all in this room. So pathologists, they're just not able to meet demand all the time. So in the UK departments, what that means is having to outsource work or bring in temporary locums to meet demand. We're actually one of the countries in the best positions worldwide for this. So most countries have fewer pathologists than we have in the UK. So if we're struggling this much, it really is a worldwide issue. Ovarian cancer subtyping, which is the thing I'll be talking about mostly, is really difficult from your standard H&E slides. So even your gynecological pathology experts will only get up to about 90% accuracy, and most pathologists are not gynecological experts. So what they will do is they'll go for a second opinion, so they'll have to send their slide or send a digitized version of the slide off to the gynecological expert. Or the other thing they can do is IHC staining, and obviously both of these options, they are costly, they're slow, so just anything extra you have to do in that diagnostic pipeline slows everything down and incurs extra costs. So what we'd like to do is make a second opinion sort of available to them straight away, and especially in low resource settings where a gynecological pathologist just won't be available no matter how far you send it. Second opinions from AI could be really, really beneficial in those settings. When I'm talking about subtypes, what I mean is these 5 things here. So they are morphological subtypes. So the pathologists have worked out what these different things are without the help of AI. They've done that themselves by really digging into different histological features that are in here. I'm not going to go through the very specifics of this because to some extent I don't really understand all of the technical differences. This really is the world of of the pathologist really knowing very small cellular details that I personally don't understand every little bit of. There's 5 main ones here, the most common one being high-grade serous carcinoma. These are all different types of carcinoma. Rare subtypes do exist, and we just can't get enough data to deal with that, so that is just an inherent limitation of what we can do. But the reason we care about these is because just these morphologies tell us things about the genetics, the treatment options, and the prognosis of these different cancers. So they're essentially entirely different cancers that happen to all occur in the ovaries. So we need to know which of these a person has to give them the correct treatment. And obviously, we need to know this quickly to get them the right treatment as soon as possible. So previous to our work, so we ran a systematic review to find out what had been done in ovarian cancer AI more sort of generally within histopathology. We were only able to find 45 published studies up to about a year ago. So quite a small sort of field compared to sort of your breast cancers, your bowel cancers. It's a much smaller field because it is a slightly rarer cancer, being only the 8th most common rather than like sort of think breast cancer the first most common in women. Not certain on that, don't quote me. But yeah, so we get a lot less published research, and subtyping, which I care about particularly, there were only 7 reported models for that at the time. So really not something that people have done a lot of previously. And the research that had been done, it was largely early prototyping, so people had managed to get hold of a couple hundred slides and try out something that seemed interesting. They haven't been able to do any sort of large-scale validation, and they've not managed to look into how robust their models were in any reasonable way. So basically, they showed that the idea has promise, but they didn't show that there was any sort of clinical utility to it yet. So where we come in Leeds, so Katie Allen, the pathologist in Leeds, she's doing a fantastic job collating this, the Bramwell Ovarian Cancer Digital Pathology Repository. The Bramwells being the family who have graciously funded a lot of this research. So something they have funded very directly is the collection of this data. So the end goal of this is a 1,000 patient cohort with 40 times whole slide images, 40 times magnification, that is. So this would be absolutely unheard of in terms of scale for ovarian cancer. So we're currently starting to work with sort of 1,000 whole slides or 2,000 whole slides, but that's only from a few hundred patients. So to get 1,000 patients would be absolutely massive, and we are working towards that. So for each patient, the main thing we will always have a primary or interval debulking surgery sample. So that is when the ovaries have actually been taken out. We always have that sample. We may also have biopsies, cytology, and metastases, and they will provide obviously a lot of extra information we can work with. And for all of this, we also have a lot of clinical data, so your diagnosis, treatment, outcome, demographics, and for some of them we have some genetic data as well. So it really is something that can do a lot of different things, and as I said, we're focused on subtyping, which is these big primary or interval debulking surgery samples, so big pieces of tissue directly from the ovary. Now, we all know it working in pathology. The issue we face is that pathology slides are massive. So you take this inch by inch piece of tissue, you scan it in at 40 times magnification, it becomes so much bigger, it becomes gigabytes of information. If you were to print this out on a standard printer, it'd be the size of a tennis court. And we're working on thousands of these, so thousands of tennis courts of information to get through. How do we deal with it? The approach we use is a very standard one, attention-based multiple instance learning. When you're talking about multiple instance learning, what you mean in pathology is just take patches from the whole slide, work on those patches, and then at the end, bring together all the information you learned at patch level to work out something about the whole slide level. So if we walk through this pipeline, on the left, we have our whole slide image input. What we want to know for this whole slide is which subtype of ovarian cancer is present within the slide as a whole. We're not trying to do anything at the pixel level. We're not trying to do a segmentation. We want to just know a subtype label for this entire slide. First thing we do is just remove the background. That's a fairly simple process. All we're doing there is basically working on how much color is in each pixel. So if there's a lot of color in each pixel, it's foreground. If there's not a lot of color, it's background. That's really simple. We then take our patches. So typically it will be 256 by 256 pixels by the 3 color channels that you have in an RGB image. We pass it through some sort of encoder. That could be a CNN, it could be a vision transformer, and that squeezes it down to a much smaller, manageable size. So in this example, our 256 by 256 by 3, that gets compressed down to a 1 by 1000 vector, which is about 1/200th of the size. So it's a massive compression. It it makes it possible to work with this data. The patch features are passed through an attention mechanism. That is a trainable part of the neural network model. And what the attention mechanism does is it assigns the patch features a single number between 0 and 1. So if your patch feature gets a low attention score, the model is essentially saying it's not that relevant to the diagnosis we're trying to make. So a low attention score means here it's not relevant to the subtype the person has. A high attention score, close to 1, shows a high importance of that piece of tissue within that patch. Yeah?
Is the subtype at the case level? Or
the subtype is at the case level. We're modelling it at the whole slide level, but yes, it is at the case level.
So a patient can have multiple subtypes in the tissue or not?
A patient will not have multiple subtypes in our data. It is a rare thing that does occur in the real world. It's not something we're currently capable of modelling. But yeah, it is rare, so we are currently focused on single subtype per patient. So once we have the attention scores associated with our patch scores, all we do is take an attention weighted average of these patch features to generate the whole slide features. So about a 1 by 1,000 vector to represent the whole slide. Yes?
We have covered it already, but maybe I can pick it up. How did the pathologists come to these subtypes?
So the subtypes are sort of when the World Health Organization defines things where you have to look out for this list of sort of 10 different features that are within these slides, go down a sort of tree of different potential diagnoses. Yeah, it's all entirely defined, but it is quite difficult to actually pick out the things in the real world compared to how they are defined. So there is some subjectivity in it.
But how did they come to what to look for?
Well, that is probably beyond what I could really explain. So it's decades of work have gone into trying to associate all these different potential pathological features with sort of different outcomes. So yeah, I can't really give you much more information than that. It's a very pathology focused sort of issue.
So one thing on this, like with the breast cancer grading, there are studies where they look at this is subjective thing. So what's the agreement between the pathologists on deciding this? Is there any number you have on these?
I don't have a single number because the people who have looked into it have come up with all sorts of different numbers. So yeah, I would estimate somewhere around 80% into rate of agreement. So there is still quite a lot of disagreement in this. And sort of one of the hopes with this sort of tool is that we can try and sort of standardize it a bit better so that we're trying to get more sort of consistent results.
On this point, we also have a question from Buzz Online who said, were rarer subtypes included in the dataset tool? If not, what would the model do if given a tumour outside of the subtypes in its data?
Yeah.
And also about IHC slides, or is it just H&E?
This is all H&E that we're working on at the minute, so that is on purpose because we always have H&E for every single one of these cases. We don't have to have it IHC, so it's trying to simplify that pipeline. In terms of sort of other carcinoma types, so we have the 5 most common here, but if another one occurs, currently the model would classify it as one of the 5, so obviously that would be incorrect. So what people are sort of pushing towards is just having an other class, so a 6th class that encompasses everything that is not one of the 5. So the other group that's working a lot on this is based in UBC in Vancouver, and they just ran a challenge where they did the 5 subtypes plus a class which was other, which included all of the rare types, because we can't get enough data for any one rare subtype to actually make it sort of classifiable. So yeah, continuing.
Thank you, Jack. Yeah, that's brilliant.
Thank you. So yeah, just continuing down the pipeline from the whole slide features. So once you have your whole slide features, you classify them however you want. So you can use any machine learning model at that point. We use a fully connected neural network with 5 outputs being the 5 classes. So that's what I was just saying. We can only classify those 5 classes at the minute, but it would be good to have some sort of way to figure out if it was an other class. The nice thing that comes out of attention-based methods is attention heat maps. So each patch got that score between 0 and 1 to tell us how useful it is. So in this plot on the right, if it got a low attention score close to 0, it got given a sort of blue colouring. If it got a high attention score, it got a red colouring. So your high attention regions are generally the areas that have a lot of tumour in them, which makes a lot of sense. Your low attention regions are your sort of loose connective tissue. It doesn't tell you anything about what cancer is there. So that's quite nice. It makes us able to sort of verify that it's doing something sensible. But this is a really sort of hot topic in terms of how much use are these things. So I've made the references a lot bigger on this slide so you can see the titles. So one of the titles, attention is not explanation. And another title, attention is not explanation. People are really disagreeing on how much value these things have. I sort of lean towards the attention is not explanation side of things. I think we need a lot better methods to really interrogate what these models are doing. I think you can easily get confused by this and sort of just looking and going, oh, well, it looks sensible, so the model's right. And actually, when we've showed these things to pathologists, a lot of the time they go, yeah, that looks reasonable, and the classification is completely wrong. So you can easily just get sort of showing something that looks nice, think it's right. It doesn't necessarily mean the model is doing something sensible.
What sort of methods do you propose in opposition?
So yeah, there's not one good answer to this. What I would like to do more is look into features specifically. So because we're working on very automated generated features, what I'd like to do is try and correlate those with known pathological features. So yeah, I'd like to know more about the features, but I don't think there's one good answer to this question. And I think that's why people rely on these so much, because they are an attempt at an answer.
So you also have access to clinical features, like some measures of the morphological attributes.
So I don't with this particular data set at the minute. So yeah, it would require some like proper labeling or it would require some automatic models people have made to that end. So moving on to a bit of work that I did early in the PhD. So this isn't the best work, just putting that out there straight away. So what we wanted to do is start using this data more efficiently. So I said how large these slides are. Basically in these slides, there's loads of motor tumour pretty much always. So we probably don't need to look at the entire thing, but how do we know where to look? So using at least a partially pre-trained attention-based model, we can take some random samples, look at their attention scores, and from those attention scores say, is this a region that we are interested in? If it is a high attention region, we will take more samples in that area. So if we've sampled a good piece of tissue, we'll sample more around it. If we've sampled a piece of tissue that's not of interest, we will not take many more samples around it. So that's what this active sampling approach is. It's take some at random, see if they're any good, and if they are, sample more nearby. So we called this discriminative region active sampling in multiple instance learning. And it was okay. It was, so if we look in the top right, we can see what it did in terms of accuracy. So this one was only a binary classification of the most common subtype versus the others, because we just didn't have much data at this point. We were sampling about 5% of the total tissue area. So it really is quite a small proportion that we're sampling here. And the box in the top right, you see that the no sampling is just your default approach by taking all of the available tissue. It gave 80.1% balanced accuracy. The active sampling approach brought that down by 1%, but it's only using 5% as much tissue. So you're throwing away 95% of your information and still nearly always getting the same result. So the real benefit of that is in efficiency. So in inference time, it takes about a third as long to classify a slide. So that's sort of what we'd like to do with these models is actually take them to the clinic so that they're not having to export their slides. There's no sort of data security issues. A lot of the time, if you're uploading a slide somewhere, it's going to America, and that's then causing a lot of issues to do with where that data is being stored and whether it's actually allowed to be there. So what we'd like to do is be able to take these models to the clinic, and they don't have the same sort of hardware we do. They don't have high performance computers. So that's why we're measuring these inference times here. So if they have a GPU in the clinic, which maybe they can afford, maybe that's an acceptable sort of burden, then yeah, it brings it down to a third of the runtime. If they can't afford that GPU, so they're only using a CPU machine, it brings it down to 14% of the runtime. So if you were to try and classify a single slide without a GPU, it'd take over half an hour. Whereas if you do it with this sampling approach, it brings that down to 5 minutes, and that's a lot more sort of viable for the clinical workflow. And obviously, as I said, that does sacrifice 1% accuracy, so you don't really want to sacrifice anything, but this is really a trade-off here. And actually, the more I've thought about this method, the more I don't think it was the correct method. So what I think and what I've seen people do a lot sort of more nicely than what I presented here is look at low resolution first and work out from the low resolution, look at all of it at low resolution and work out where the sort of important tissue is there. And then from that, you've looked at everything, you can really dig into the bits at high resolution that you found to be important at low resolution. Because the issue with this approach, you could just miss something. It is possible that you just happen to randomly sample with and miss an important area that told you the diagnosis. Whereas if you were to look at everything at low resolution, you wouldn't miss that important region.
Sorry, can I?
Yep.
That's a good question. Okay, so with this grass cell.
Yeah.
Do you first do one round of random
Yeah.
selection and another round of sampling around those high attention ones?
Yeah, we ended up doing it sort of more than just one iteration, but yeah, it turned out that if we do it over and over again, taking the new information offline to every sample, it's slightly better. So,
But
yeah,
these
that's
numbers
the
that you
idea.
put in here, how many rounds of sampling?
This was around 10 rounds of sampling, with each one doing about 0.5% of the entire slide area, which is how we get to about 5%. So, as I was mentioning, magnifications there, talking about sort of low magnifications and high magnifications. So what I'm showing here is how there is so much difference in what you can see at these different magnifications. So 40 times the highest magnification that the clinicians do actually use, so we scan everything in at that magnification, is very, very cellular. So you're looking right into the nucleus at that point, you're seeing really deeply into the cell. Whereas if you bring that down a bit, sort of 5 times, 2.5 times, you're seeing a lot more of the histo-architectural context. So how these cells are put together into sort of tumor areas, into stroma areas. So the issue with the attention-based multiple instance learning models is that they see each patch as entirely independent of every other patch. So if you're really digging into that sort of high magnification, it loses track of where everything is in relation to each other. It loses the context. So if you run it at a lower magnification, it can then account for that. So at a low magnification, it can probably still see quite well what the cells are doing individually, but then it also gains that wider context. So people have looked at this quite a lot. A lot of people do just use 20 times as a default, and sometimes it's just because it feels right, or they've had a little go with it and found that it was okay. Some people have tried to dig into it and generally found that different magnifications do different things for different tasks and for different sort of cancers. And in ovarian cancer, it really isn't clear which magnification we should be using or whether it's multiple magnifications. So what we did was evaluate these 6 magnifications from 40 times at the highest magnification to 1.25 times at the lowest. That would obviously be sort of, we don't expect 1.25 times to be the solution to this, because it really is just like looking at it very, very zoomed out. It won't get all the detail right. But what was interesting is in this bar chart on the right, the worst one we had was 40 times. So the highest possible magnification was not the best for this. The best we got was around 10 times or 5 times. As you can see, it's quite wide confidence intervals. So all we can really conclude is that there's not a big difference when you change the magnification, but it does appear that 10 times might be beneficial, yes.
So on the previous slide, your numbers were balanced accuracy, it was 80%.
Oh, when I had the 80%, that was binary classification of the most common subtype against all others. This is now a proper 5-class classification, which is why we're now looking at lower numbers.
Thanks.
So what we've concluded is that 10 times is pretty good. And the great thing about using 10 times is shown in the bottom right. So training time goes down from 3 hours 45 to 13 minutes. So that's 5% of the time trained. So that means we can start doing things like proper hyperparameter tuning, or we can just use less of our computational power, so we can save the planet a little bit. Inference time as well, as I said before, we like smaller inference time so that it's more realistic. We can actually deploy these things clinically. So it brings it down from 7.5 minutes to 3 minutes, which is about 40% of the time. So we're really making big savings here and still getting at least as good results, if not slightly better. So as we just saw, the balanced accuracy wasn't great at this stage, and basically it was a reasonably small data set. It was actually still one of the largest used in the field. But what we want to do is figure out, well, what can we do to get more data? So one of the issues we face is that we do have a lot of nice pre-chemo data, which is what the pathologists really want to look at, but that's not always available. So a lot of patients will have chemotherapy before their surgery, but that will really degrade the quality of the tissue. So we want to find out, can we still use this tissue in a sort of useful way? So the degradation you see is because the tumour has been made smaller to some extent, so a lot of it's been killed, it's actually shrunk the tumour down, and also just the dying tumour cells take on a different sort of pattern, different shape, so it's not the same as what you see in a sort of healthy tumour, which is what we're trying to do.
There, these disease classes, are these available for TCGA?
No, unfortunately not. TCGA only does serous ovarian carcinomas, which is, it does cover 2 of our classes. It covers high-grade and low-grade serous, but high-grade serous is 90+% of their samples, and they only have 100 formalin fixed ovarian samples. So unfortunately, TCGA is not a great resource for this. What we wanted to do is find out if the post-chemotherapy data was useful to us. So previously we were training and testing using only pre-chemo. Here we're still testing using only the pre-chemo data, but we want to see what happens if we add more data. So starting from our smallest data set of pre-chemo only, we only get 53.4% balanced accuracy. Now that is balanced across 5 classes, so that's not quite as bad as it might first appear, but it's still not good. So if we add in extra pre-chemo data, so more of our really high quality data, that goes up by about 12%. But if instead of pre-chemo, we add in extra post-chemo data of the same quantity, we still gain 10% balanced accuracy. So it's quite similar between the two. It's very slightly better to add more of the highest quality data, but really we're at a point where any extra data is still beneficial. So what this is saying to us is just put both of these data types in there, just make our data set as big as possible to get the best returns. And that all leads into the most exciting part of all of this, is the foundation model. So how do we get the most bang for our buck with the data we do have? Well, I would say that it's probably not the ImageNet pre-training that we have in the top right there. So that's your pictures of cats and dogs, cars and planes. It's your natural images that everyone's been using to generate sort of generic features for the last 10+ years. So that is fantastic in that it can be applied to a lot of tasks, but it's not perfect for pathology because there's a lot of different sort of colours and shapes in the ImageNet that just don't apply to histopathology. So pathology works in pinks and purples, talking about H&E specifically here, works in pinks and purples, and very small differences in sort of circular shapes can have really important consequences. So there's a very specific feature set to histopathology that just won't be captured in ImageNet. It's trying to be very broad, it's trying to be very generic. So that's what people are working on in foundation models now, is trying to make that very histopathology specific feature set. What they're generally doing is using vision transformers. So transformers have obviously been very exciting in the last few years in terms of text models, so your GPTs of the world, and we're seeing that bigger is better. So like put more data in, make the biggest transformer you can, you get really good results out of it. That seems to also be the case for vision transformers, or at least that's what people are trying out, and at the minute it's probably still scaling in that way. And they're doing large domain-specific pre-trainings. So yeah, that's moving on from CNNs to vision transformers. So what we did is we took a whole bunch of these feature extractors. The first 3 are your ImageNet pre-trained feature extractors, so a ResNet 50, ResNet 18, and a vision transformer. And then the next 14 are all histopathology foundation models that have been made available online. So I didn't make any of these, I'm trying them out to see how they work on my data. So there is a lot of variation in what people are doing. So different backbones, generally people have started going towards vision transformers of various sizes because they seem to work well. So some of the early ones did use convolutional neural networks, but generally people aren't building those anymore because they don't seem to work as well. The data sources are quite varied, so a lot of people did use TCGA or other online data sets, but a lot of others used internal data sets to their specific locations. Pre-training algorithms, again, it seems to be converging in a way, so people tried out a bunch of different stuff, but now DynaV2 seems to be the best that we have, so people keep using that, and maybe something will replace that in the near future. Pre-training images, so that's again quite variable. So the smallest one, Python, used only 6,000 whole size pre-training. So that's a very, very small pre-training set for a foundation model. Whereas the largest ones now are actually over 3 million whole slides. So that's a huge quantity of data. That's going beyond the sort of terabytes that we're used to into sort of the petabytes. That's huge. Pre-training magnifications, again, variable, but 20 times is the most common. So people just like 20 times, it seems to work for a lot of things, but some of them are doing multi-magnification things. The number of parameters, which is how this is currently ordered, goes from about 11 million parameters to 1.1 billion parameters. So the smallest model is about 1% of the size of the largest. There really is a lot of variation here. And the largest models are all different variations of vision transformers. And patch features, generally, per patch, you're getting about 1,000 features out, but that again does vary to some extent. So what did I do with all of these? So I wanted to be as thorough as I could, and I am focused on one task, which means that I can go sort of deeper than when people are trying to look at loads of different tasks. So what I can do with this, first of all, just a 5-fold cross-validation on all of my data. So my training set is nearly 2,000 whole slides from 434 patients, which for ovarian cancer, no one has done as much as that by quite an extent. So this really is kind of cutting edge for what we're doing. And then those 5-fold cross-validation models were used as ensemble models, so an average of the predictions for 3 test sets. One of them was internal, so it was held out. It was 100 slides from 30 patients. It was class balanced. And then 2 of them were external, and these were the only external data sets we were able to get. So ovarian cancer, as I said, has not been a well-trodden path so far. So the only 2 data sets we could get so far was one older one, which was about 10 years ago. They did a study in this space, which was 80 slides from 80 patients, and one more recent one from UBC in Vancouver, who just ran this challenge this year, which was 513 slides, but we're not sure how many patients. And actually, with that one, we don't know a huge amount about how the data was processed, but we do know it came from a lot of data centers. So there's a lot of variability, but we don't know a lot more than that. And the results of all of this is that all of the foundation models outperformed all ImageNet pre-trained models with one exception. The one exception was the earliest foundation model, so these orange bars on the right are all foundation models. The blue bars on the left are all ImageNet pre-trained feature extractors. The one exception, ResNet 18 here, so it was one of the earliest foundation models. It was the smallest foundation model. It had a small pre-trained data set. And with it being an early approach, it just didn't have access to all the techniques we now have. So I'm not particularly worried that that one didn't live up to the other ones because it was just an early one. But after that, all of the more recent ones have done a lot better than ImageNet pre-training, and by a fair extent as well. So our best ImageNet pre-trained model was the vision transformer. So we're already seeing vision transformers are doing better than convolutional networks. And that had these balanced accuracies I've shown here. But the best overall model, one of the foundation models called H Optimus 0, the balanced accuracy was a lot better. So on the cross-validation, it went from 63% to 72%. On the holdout test set, it went from 76% to 89%. On the first external test set, the Trans-Canadian study, it went from 81% to 97% balanced accuracy. And on the second external test set, it went from 60% to 74%. So these are massive, massive gains we're getting from using these better features. There's quite a lot of variation in these results. We think that the reason for that is the thing I was talking about earlier about pre-chemo versus post-chemo. So the test sets where we got the worst performance had a lot of post-chemo data in it. So a lot of the data had been affected by the chemotherapy, and that made it harder to classify. So that is something we really need to dig into deeper, is what can we do about that? How can we classify these post-chemo samples better? Yeah.
That's a question. First, when you were on pre and post chemo, I had this question in mind before. So does it change the subtypes?
It doesn't change the subtype, no.
And do they look similar when you look at them? I mean, you mentioned that they don't, right?
Yes, there is a lot of difference, and yeah, it's because the tumour's been made smaller and the actual tumour cells have been attacked in a way, so like a lot of them are dying.
Okay. But so with post chemo, is it all the subtypes and have post chemo samples in them, or just
yes.
some specific subtypes?
It can be all of them. It probably does vary to some extent, so there's probably certain ones where it happens to all people getting chemo, but the standard pipeline now generally does have people getting chemo before surgery.
And one more quick question. So what I see here is that when you go from cross-validation to internal validation and then external validation, what's happening, especially about 3 first numbers, so you get better results. Because, usually what we see is the other way
Yeah.
around, right? What's happening there? But
Yeah.
is it because your data is harder to work with, the internal data, or what do you think?
Yeah, so I do think that it's because our data is just harder to work with. So it's that same pre versus post chemo. So the cross validation, the first number, it had a lot of post chemo data in there. So like a lot of it is just inherently difficult to classify. Whereas the holdout test set and the Trans-Canadian study didn't have any post chemo. It was all the sort of highest quality pre chemo. So the most likely to be classified correctly by a decent model.
Other than increasing the size of the data set, I don't see the point of doing subtyping over patients who've already been given chemo. Because as I understand, this subtyping would be used to determine what type of treatment to give to the patient, and they've already received that treatment. So what's the clinical advantage of generating subtype predictions for these patients?
Yeah, so you certainly do get more utility in the pre-chemo patients, as you say, because they've not received any chemo yet, so you can really tailor it. But the patients who have received chemo, they've received 3 rounds out of 6 rounds of chemo, so that can still be altered if it needs to be. There's also immunotherapies that are available, which may or may not be beneficial to certain patients. So there are other types of treatment than just the chemo that may or may not benefit certain patients. So even if they've received some chemo before their surgery, it's still beneficial to know their subtype.
I think linked to Faiz's point, so Buzz has asked the question, well, I said, if you had a good chemo data set and outcome data, you could predict tumour response to chemo, which would be very cool.
Yeah.
But he's also said if you've got no data, but it's thought tumours, sorry Buzz, no data, but it's thought tumours which show large morphological changes are chemo responsive. And that's more of a comment to Buzz.
Yeah, so I mean, people are starting to look into things like treatment response with this type of data. It's still early stage, but yeah, it could work, it could not work. I'm not certain at this stage, but yeah, certainly an interesting research question.
And Craig's also asked, do you have any intuition as to why H optimus 0 is the best overall model?
I'll start digging into that, so in that one. So, first thing we looked into after getting the results was the scale. So bigger is better to some extent. So if we look at the image on the left, that's the actual size of the model in terms of model parameters against the balance accuracy in each of the 4 validations. So that's your 4 different colours and your 4 different lines. We had a positive trend for 3 of the 4 validations. So they were fairly weak correlations between 0.3 and 0.36 correlation coefficient. So that is saying bigger is better, but there is definitely a lot of other things going on as well that are making a difference. One of those other things that is making some difference is the size of the pre-training data set. So again, it was only 3 of the 4 validations where we really saw an effect, and that effect was even weaker for the number of slides used in pre-training. So between 0.14 and 0.24 correlation coefficient. So bigger is better, but it's certainly not the only thing that's going on. There's certainly got to be other things that are making a difference. One of the models that we did see do consistently well was Uni. So Uni was the only model in which all of these results did better than you would expect. So that's basically them being above the line for each of these validations. So Uni was better than expected for the number of model parameters and the number of poll slides used in model training. What we did think that might be is to do with the composition of the pre-training data set. Turns out, no, it's not. So we looked at how many ovarian cancer slides they were using and how many gynecological slides. It was no different to any other foundation model that reported on that. So there were other models that used more ovarian cancer slides in their pre-training that didn't do as well as Uni. So there's something else going on that we can't quite figure out right now. So yeah, if anyone has answers to that, then that would be very interesting. But it's very much an open question into which ones of these do well and why. So on this results table, what I've done is averaged the results of the 4 validations. So it's not inherently that meaningful, but it does give us a bit of an idea of which model is best. So this is why I said that Optimus was our best model, because it had the best balance accuracy when we averaged across the 4 validations. But there are alternatives that also do well. So Virchow to 82.6% is very, very close, and actually has a slightly higher AUC if that's your sort of metric of interest. And there are some others that I've highlighted here that did really well for their model size. So this is still ordered by the size of the model. So the ones down here are massive, massive models. ones at the top are really small models, and actually that generally show that those ones do very well. But there's some in the middle here that actually hits a really nice middle ground, and Uni especially did nearly as well as this massive model here, but was much, much smaller, so a lot more efficient to work with. Something else that we looked into was tuning the attention-based multiple instance learning model. So we are not doing anything to the feature extractors here. We just extracted the features as frozen feature extractors, and then we are tuning the multiple instance learning model afterwards. So we tuned 10 hyperparameters, which relate to things like learning rate, optimization, regularization, and model size. And for each of the models, it was over 150 total configurations. So this is still a lot of computational overhead. So we did it in an iterative approach where you keep most of the hyperparameters the same, but 2 or 3 of the hyperparameters, you give them a larger option and a smaller option, and then find which of those work best, move on to some other hyperparameters. So it's really computationally intensive. You have to be a bit careful about how you go about this. What we did find though is that tuning was helpful. So you can see that the losses were coming down quite nicely. And the losses actually shot down in the first few tuning iterations. So you probably don't need to do this as thoroughly as I did it to get good results out of it. Yeah.
But does it also affect the final accuracy that you get?
Good question. It does also affect the final accuracy. So the downstream results were improved by a median balanced accuracy of 1.9%. So if you tune, you get very slightly better results. I mean, yeah, 2% can be important or it can not be important compared to other things you're changing. But I think hyperparameter tuning is really important when we're saying that one model is better than another model. I think there are too many validations right now that are comparing without hyperparameter tuning. So it might happen to pick the worst possible hyperparameters for one of your models, but you picked really good ones for another one, and you're then saying this model is really good. I think that's not a fair comparison. The improvements that we got from tuning, so the improvement was absolutely very variable from minus 0.6% balance accuracy to plus 15%. So some of them actually did worse from tuning, but the only time we found statistical significance was when we found an improvement in the balance accuracy. So it does appear that the balance accuracy is statistically improved by tuning, but it is variable and it doesn't always happen. What you're looking at on the right there is the pink bars are balance accuracy before tuning, the blue bars are after tuning. So if you see the blue bar higher than the pink bar, it is improved performance. If you see it the other way around, it is harmed performance. So the only times we get these stars, which are the statistically significant improvements, is when after tuning did better than before tuning. So we're getting a benefit.
Sorry, just
Yeah.
my own knowledge. What test did you use for statistical significance?
Oh, I think it was a t-test on the 5-fold models. It's in the paper if you want to dig into it deeper, but I'm pretty sure it's a t-test. So some just sort of wider considerations about foundation models. So as I said before, we're not certain what makes a good foundation model. I will say on this slide, if you're interested in foundation models, do look at these down here. So we've got some really interesting references. So Heather Couture did a really good talk a couple of weeks ago at MICI about foundation models. We also have, where was 2 gone? So Peter Neidlinger did their talk a couple of weeks ago here, wasn't it, at the TIA seminar? So that's on YouTube. Watch that. That was fantastic. Gabriele Campanella does a lot of good work on this and has recently published a benchmarking paper, which was somewhat different to what we did. It was a lot more sort of broad scope rather than deep scope. So that again is interesting. I'll talk about reference 4 when I get further down the page. So yeah, from all of these references, what we can say is we're not certain what makes a good foundation model. There are some things that make some effect, but there's certainly some things that we're not currently realizing are important. It's also unclear which one is best for any given task or multiple instance learning approach. So the results I've got probably do generalize fairly well to other ovarian cancer subtyping. They may well generalize well to other subtyping tasks in other cancers. They probably don't generalize well to prognostication in different cancers. It probably is somewhat task dependent, and it probably is somewhat multiple instance learning approach dependent. So we used attention-based multiple instance learning here. You could use all sorts of different approaches, and it probably makes a difference. We didn't look at any vision language foundation models here, and they do work slightly differently and could come up with different results. And the big issue really is the huge computational burden. So I did 14 different foundation models. It was an absolute nightmare to run all those on all of my data. So people are trying to come up with more efficient ways to assess whether a foundation model will work for them. That's where reference 4 comes in. So George Bachkala gave a good talk at MICI a couple of weeks ago. His idea is basically take a small subset of your data, sort of 5% of your data, put it through all of the foundation models of interest, and just cluster on the output of interest. So, or whatever you're trying to classify, just do clustering. Whichever one clusters best, hopefully will turn out to be the best foundation model for your task. I know he's still validating whether that actually applies as well as we hope it does, but that's a really neat idea, and it'd be nice to see more ideas like that to test out these models without having to do them so thoroughly. I did mention earlier that heat maps can be a bit sort of difficult to work with. So we showed orthologist heat maps from ResNet 50 and the Uni. So these are sort of opposite ends of the spectrum where the ImageNet pre-trained ResNet didn't do very well. The Uni model did really well. We showed them the heat maps where the classification differed. They couldn't tell which one the better heat map was when they were comparing them side by side. They didn't know which one gave the right classification and which one gave the wrong classification. So heat maps alone do not give you enough information to really say what's going on behind the scenes. Just going to quickly run through some of my other work, which isn't quite as interesting, but it's still quite cool. So first of all, multi-resolution patch graphs. So the issue I mentioned with attention-based multiple instance learning is that it loses all context. It treats each patch as independent when they clearly aren't in reality. So we looked at multiple magnifications. The low magnification is generally about 5 times and the high is about 10 times. We take the neighboring patches and we connect them together in a graph. We then connect in between the magnifications as well. So each low magnification patch connects to 4 high magnification patches, which all contain the same tissue at a different magnification. We then adjust our multiple instance learning pipeline to accommodate this. So we add in graph attention convolutions, which are the things that pass the messages on the graph between the neighbors. And we add in self-attention graph pooling layers, which take the graph, get rid of the less important bits and squeeze it all together into a small graph. What we do get in the final box, the slide classification box, is a feature set that is twice as big as it was before, because we need to keep our low magnification and high magnification features separate, because if we merge them together, they start to lose their meaning within their certain sort of magnifications. And when we validate this, what we find is that the graph only outperforms attention-based multiple instance learning in one validation, and in that validation, it went from 97% to 99%. Now, considering that one where it did find improvement only had 80 slides to begin with, over this entire 2,500 slides, we're sort of improving by 1. Like, we've gone from classifying sort of, I think sort of 1,800 of them correctly to 1,801 of them correctly. So the graphs have not made a big difference to us. What I would say is that graphs probably do make a big difference if you're doing prognostication. For subtyping, actually, I think all you need to do is get the best possible features at patch level and put them into any multiple instance learning model and you'll get good results. I think that graphs are overkill for what we're doing, and that's what we found in these results. So what we did find was that, again, the foundation model was really beneficial. So on the bars on the rightmost bar was the only one that didn't use the new foundation model. That one used an ImageNet pre-trained ResNet. And in that case, performance absolutely plummeted compared to the foundation model. So the foundation models give you sort of 75% to 80% on this one, but it only gives you 40% if you use ImageNet pre-train. And on the top one, it goes from about 75, 80%. Up to a maximum of 99% when you're using the foundation model. So again, the foundation model is really important, but the multiple instance learning approach you use afterwards, not so important. And the last piece of work I'll talk about, this isn't my work specifically, this is Katie Allen from Leeds, the pathologist. So she's using very similar approaches to what I've done for metastasis detection. So each time a person has their ovarian cancer surgery, there will be dozens of slides to review. A lot of them will be lymph nodes and omentum being a layer of fatty tissue over the peritoneum. And they do tend to collect metastases, so like they do need to be looked through all of these different slides from these tissues. But a lot of the time, there's just nothing there. Pathologists are having to really deeply look at like these lymph nodes that have nothing in them. So obviously that's a bit of a frustrating task, it's very slow. So we did a malignancy classification. This is very much like the chameleon challenge, if people are aware of that. So that was in breast cancer, but this is ovarian. And we're getting really promising early results. So this is all internal so far, so we need to validate this more thoroughly. But so far, we're getting 95% internal balance accuracy on momentum and 100% on lymph nodes. So if that generalizes, this is fantastic. This is a lot easier to put into a clinical workflow than the subtyping work I've been talking about. So actually, this is something that might be able to make a difference in the near future. And talking of implementation, so my final slide. So there was a nice paper that came out recently that showed that there was only 26 approved by regulation path AI tools in the UK or EU. So and it was even less in the US. So really, it's an early stage of regulatory approval for these things. All of them targeted the most common cancers, so none of them were for ovarian cancer. And nearly half the things that have been approved, there wasn't even any public research out on these things to say whether they did work properly. And none of them had yet been associated with prospective research. So I know that like Page AI are now working on that sort of thing, but it really is sort of, for the size of like the research that people are doing, there's not a lot that is yet reaching clinical translation. So that's something we really need to think about, is how do we take this and put it in the pathologist workflow in a way that actually benefits them. So again, thinking about those attention heat maps. Do they help pathologists? I suspect not, but we need to run those studies where we put them in front of pathologists and say, has this helped you? Are you now more confident? Actually look at them numerically. Have you now made the right classification? And look at how long it takes them, because if it really slows them down, it might not be worth it. So we need to do a lot more to see whether these things are applicable in practice.
Good question. Is
Yes.
Uni multi-resolutional? So you would already use its multiple.
Uni.
Yeah.
Uni was pre-trained at 20x only. I actually applied it at 10x though, and it worked absolutely fantastic. So
your graph features, when you compute your Uni features and multiple resolutions, you use the same 20x trained.
correct, yes. And yeah, that's it for the slides. So thank you very much for listening. You can get in contact with me on any of these things, and you can obviously ask me questions in the room or online. Thank you very much.
Well, thank you very much, Jack. That was a brilliant talk. Does anyone have any questions?
Yeah, I have a question. Can you hear me?
Yeah, we can hear you okay, Daniel.
Excellent, great. So there was a really great talk. Thanks a lot. I've actually just been looking into using foundation models in our task, which involves semantic segmentation. So it's a bit different, I'm aware, but it was really nice seeing kind of like a comparison between all these different foundation models. I just have a couple of questions. So one of them is, I mean, I had a quick look through the paper, and I see that you tried applying stain normalization to the ImageNet pre-trained models.
Yes.
Did you try applying that to any of the, like when you use any of the foundation models? Is that something that you think might help improve performance?
Yeah, so just to bring everyone else up to speed on what is being talked about here, I have prepared a slide on this. So what we did try is, can we make the ImageNet pre-trained ResNet as good as the other models by using things like normalization and augmentation? So we take the bar on the very left, the ImageNet pre-trained ResNet 50, and we apply our augmentations or normalizations, and we get those green bars in the middle. Now, those green bars in the middle still aren't as good as the orange bars on the right, which are the foundation models. So basically, these ResNet features are still not as good. There is not a lot we can do to them to make them as good as foundation features. So the question being asked is, could we try those same augmentations, normalizations on foundation models? Yes, we absolutely can. It might improve performance. I haven't tried it myself, so it's certainly an area that could be interesting. I think that it probably wouldn't make as much difference as it makes to the ImageNet pre-trained models, because basically it's already somewhat baked in by the fact that we've done all of this massive pre-training. So I don't think it will be as important, but it certainly is worth looking into.
Okay, great. Thanks. That's really clear. And then I have another question. If I did want to use Uni, so like what I've used actually so far is the ResNet 50, but not the ImageNet trained one, but the non-ImageNet trained one. And I was thinking of using one of the vision transformers, but I'm just concerned about its computational requirements. I was just wondering, like when you did use Uni, what sort of GPU did you use, or what would you recommend for Uni, for example?
So I was actually working on quite a big GPU at that point, and that is something that's worth taking into account. So if we go all the way back to these results, so you can see that like the ones at the top are the smaller models. So you can see that some of those are still really good. So this Lunit model, which is the second one within the foundation models, it's smaller than a ResNet 50, but it gives a lot better results. C-Transpath as well, it's a smaller model that gives better results. Yeah, it's basically try out some of these and see which ones of them actually work for you computationally, because you don't have to use the biggest one. Certainly, if you're struggling computationally, don't use H-Optimus 0. It's absolutely massive. So yeah, if you can make uni work on your, do it. If not, try one of the smaller ones.
Okay, great. Awesome. Thanks a lot.
Thank you.
So have you shown some of the predictions that the model was very strong on to pathologists, if they would agree with the new label that your model has assigned, or no?
So we've not used it for relabeling data. I think that's what you might be getting at. So we've assumed that the labels we have are correct because they've been sort of thoroughly done. But so they were originally labeled by a gynecological expert. They were then checked again by a second pathologist. They're not going to be perfect. We know that, but we're hoping that they're accurate enough that we don't have to relabel things. It's certainly something that would be interesting to look into which ones it disagrees with and then see if any of them need changing. We've not done it.
Do you have any advice as to, so obviously you talked about feature extractors here mostly, but in terms of actual aggregation algorithms, so whether to use attention-based or transformers, have you got any overall advice or
Yeah,
recommendations?
so I'd say basically for this sort of subtyping, you can keep it simple, and I think it's the simple approach there. So transformers probably do help for certain tasks, but not for others. I think actually it's not that important compared to the feature extractor.
Yeah, so also a good question
Yeah.
related to these. You've mentioned that overall the short was both better. When you see the fine tuning, is it still not the best one?
This is after the hyperparameter tuning.
Oh, outside.
Yes.
And also wanted to know your experience with batch size. So how effective was changing batch size on the resource you get the different?
I've not looked into it, so
During the hyperparameter selection batch
I
size
didn't
was
include that as a hyperparameter, so it's a good point. I should have included it. Yeah, I didn't think of it.
Oh, that's right. Interesting, yeah. Thank you. What Noor says also, that would be really interesting for like some of the errors that like you have
Yeah.
high confidence.
Yeah,
Maybe they did wrong. Then
absolutely. Yeah, certainly possible.
Yeah. But great job, yeah.
Thank you.
Sign. I think so. Yeah. So we've still got this room booked for longer. So if anyone's got any more questions, then feel free to stay and
I can
ask.
see a couple of hands on that as well.
So we still got some more online, haven't we? But I think that is there any more questions online?
I can
Sorry.
see where your hands are.
Yeah, can I ask?
Yeah.
Yeah, sure. Please go for
Yeah,
it.
brilliant. So that's a great talk, Jack. I really enjoyed it. I had a kind of few interrelated questions on the subtyping side of things, though. So my background's in non-small cell lung cancer, and in non-small cell lung cancer, you might have a diagnostic slide, and like in ovarian cancer, pathologists would label or sort of give a slide a histological subtype. But in the diagnostic slide, you'll actually see multiple different histological subtypes kind of within that slide. So it's spatially heterogeneous. So I was just wondering whether you looked at the prevalence of the ovarian subtypes that you've identified within these slides. And also, given that it is heterogeneous like that, at least in my background, I don't know if it is an ovarian, but if it is heterogeneous, is treating it as kind of a whole slide classification problem the appropriate treatment, or should you be looking within the slide?
Yeah, so it's certainly a lot less heterogeneous than what you're describing. So it is rare that we get mixed subtypes, but it does exist. So this probably isn't the optimal approach because mixed subtypes do exist. So yeah, I think it will end up having to be something more sort of region-based, or certainly allowing for multiple classes to be classified on the same slide. And that's something that at the minute is not capable of doing.
And are the subtypes themselves linked to outcomes or specific
Yeah.
treatment pathways?
Yes. Yeah, I mean, that's why we're interested in them, is that, yeah, what they show us is coming from genetic differences. So the cancer really does develop very differently, and then, yeah, that leads to different prognosis, different potential treatments.
So I guess relating then to my previous question, if that is true, then perhaps it is important to look kind of for rarer subtypes
Yeah.
within the slide versus the overall one, because it could be the rare kind of more dangerous one, if you like, that's leading to you know, negative outcomes.
Yeah.
And sorry, just to ask a final one on subtyping, did you try and do an unsupervised subtyping that was kind of not restricted to, you know, already defined pathologist subtypes?
So I haven't tried it. That would be interesting. What I have seen in that space is basically clustering features. And generally what I've seen is that the features do cluster into the known subtypes. So that gives us some sort of confidence that there is something sensible going on. But I've not looked into it myself. So yeah, it would be interesting to see.
Great, thanks.
Thank you.
I think we've also got Buzz's hand up. Buzz, have you got any questions? I think as we've got the room booked for a bit longer, we'll continue taking questions. If anyone does need to go though, please feel free to go.
Sorry, can you hear me?
Yeah, we can hear you, Buzz. Go for it.
Yeah, I was just wondering, did the data set include any core biopsy tissue?
No, so we specifically stuck to resections here. So biopsy actually probably is the way forward in the patients who have received chemo before their surgery. So currently that's how the pipeline actually works. If someone has their chemo before surgery, biopsy is what will be used to make this subtype classification. So yeah, it certainly could be integrated, and it hasn't been yet.
And sorry, I know you did mention it, but how many of the cases in your data set were post-chemo? Do you know?
It was approximately 500 of the 2,000.
I don't know what the stats are, but I don't know how many patients with ovarian tumors get biopsies, but usually they're the patients who are advanced, because the biopsies are never rarely ever taken from the ovaries. They're nearly always taken from an enlarged lymph node or an amental deposit. That would suggest that at least a quarter of your data set is from patients who have already had very, very bad, they're prognostically as bad as it gets, I suppose.
Yes,
So
I would agree,
that may be skewed quite heavily towards the worst subtypes of each of those fields.
Yeah. Yeah, it's just an issue with data availability, and yeah, as more data becomes available, we can hopefully be more picky about that sort of thing, but we really are struggling just to get data in the first place.
No, that's understandable. Also, do you know the heat maps that you developed, and you were saying that they would pick up specific areas? You realize even that from you were talking about useful tools, even that itself is an actual useful tool for a pathologist to have just a heat map thrown up saying, hey, look, these are the bits that are worth seeing for screening cases as part of people's routine workflow. You know, so somebody could go down, see just 5 samples of all the ovarian tumors in their department and say, hey, these are the bad ones. Let me quickly report these because these are more urgent. So even simple things that you're developing are on the ground could be incredibly helpful. It's an impressive piece of work. Thank you.
George just has to nip off, but he also had a question. He said, does pre or post menopause slides show a difference?
They will do, because it is so related to subtypes. So if someone gets ovarian cancer pre-menopause, there is a certain couple of subtypes they're much more likely to have.
Thank you. So I suppose we'll call the meeting to a close. Jack, you're a bit around for a bit longer, aren't you? So if there's any more questions, then you can find us. So, but yeah, thanks everyone online. And thanks again, Jack. That was a really good talk.